Welcome to the tutorial on current division. Before we understand how current division occurs, let me quickly brief through how a series circuit looks and how a parallel circuit looks like. In a series circuit, the various components are connected end to end. So if I consider say multiple resistors and name them as R1, R2 and R3, then there is only one path for the flow of current. That is because the resistors are connected end to end. Whereas in a parallel circuit, three resistors R1, R2 and R3 have two sets of electrical points that are common between the various components that are connected. So as you can see, this point is common to this point is common to this, whereas in this case the other end of the resistor is common to this point, to the resistor R2, and this point is common to the resistor R3. In this particular case, that is in the parallel circuit, we will have multiple paths for the flow of current. So let me explain this with an animation. In this particular circuit, we have considered three resistors which are connected end to end, and you can see there is a single path for the flow of current. Whereas in the parallel circuit, we have connected this particular lamp with the common points, that is two common points. So this is the lamp L1 and this is the lamp L2. So these two lamps have this particular points in common, and we can clearly see that there are multiple paths for the flow of current. In a parallel circuit, the voltage that appears in the parallel branch will be the same. So the voltage that appears across the lamp L1 will be same as that of the lamp L2. So I can write this as V1 to be equal to V2. So let me explain the current division rule with respect to two branch circuit. So let me consider a circuit with a current source, which I am going to name it as IS in this case, and I have two branches wherein the component resistance R1 and resistance R2 is connected. So to understand the current division rule, let me consider a simple circuit wherein I am having two branches which are connected in parallel. And as we have discussed earlier, in a parallel circuit, the current will take multiple paths. So in order to show that, I have indicated this branch current as I1, this branch current as IL. And the two resistors R1 and R2 are connected in parallel, and this is the source current. So if I want to compute, say, the current across this particular branch IL, I can compute that as IL to be equal to the resistance in the opposite branch, that is resistance R1 multiplied with the source current IS divided by the sum of all the resistors connected in parallel. So you have resistance R1 plus the resistance R2. Similarly, if I am to compute, say, the current I1, I can compute that as the resistance in the opposite branch, that is resistance R2 multiplied with the source current IS divided by the sum of all the resistances R1 and R2 in this particular case. So say I have a circuit wherein the source current is IS and I have multiple branches, say resistance R1, resistance R2, resistance R3, and so on up till say resistance Rn. Then say I want to compute the current IK which is flowing across this resistance R2. Then I can write the generalized equation as IK will be equal to 1 by RK, that is the total resistance of the opposite branch multiplied with the source current divided by all the currents that are connected in parallel. Now, it is not necessary that always the current source should be provided at the input side. We may be also provided with the voltage source, but always there will be the current that will be flowing at the input, which will become our source current. So let us consider this with an example. So here is a circuit wherein I am considering the source voltage Vs to be 10 volt, the resistance R1 to be 5 kilo ohms, and resistance R2 to be 20 kilo ohms. This particular source voltage will supply the source current that will be equal to Is, and the current that flows across the branch R1, let me denote this as I1, and that flows across the branch R2, let me denote this as the current I2. Let me consider the source current as 2.5 milliamps. So if I am supposed to be computing the value of the current I1, I have to compute it as the resistance in the opposite branch, that is R2, multiplied with the source current Is divided by R1 plus R2. So in this case it is going to be 20 kilo multiplied with 2.5 milli divided by 5 kilo plus 20 kilo ohms. So that is equal to 2 milliamps. So the current I1, as you can see, is equal to 2 milliamps. Similarly, I can compute the value of the current I2 to be equal to the resistance in the opposite branch is R1 multiplied with the source current Is divided by R1 plus R2. So I2 will be equal to 5 kilo multiplied with 2.5 milli divided by 5 kilo plus 20 kilo, that is equal to 0.5 milliamps. So in this particular circuit, they had provided us with the value of the source current Is. So the same circuit I can also draw this to be equal to Is to be equal to 2.5 milliamps with the resistance R1 and the resistance R2 being connected. And this was the current I1 and this was the current I2. So when we are to do simulations, you would be able to observe that in the multisim we do have the source current. So directly using this particular circuit, we can observe what is the current I1 and the current I2. when the current source is not provided to us, we need to compute what would be the value of the source voltage. So how do we do that? That is very simple. All you need to do is you need to compute the source voltage Vs to be equal to the current source multiplied with the equivalent resistance. So in this particular case, how do you compute the equivalent resistance? You can see the two resistances R1 and R2 are in parallel. So if I have to compute R equivalent, it is R1 parallel with R2. In this case, the two resistances are 5K parallel with 20 kilo ohms, and the source current is 2.5 milliamps. So just use the value of 2.5 milli, multiply with this equivalent resistance, and you will get the value of source voltage to be equal to 10 volts. So you will be able to see in the simulations that I am going to present to you that we can use either the current source directly and observe the branch currents, or we can use a voltage source and observe the branch currents. In both the cases, the value of the branch currents I1 and I2 will be the same. So here you can see that I have given a 10 volt supply voltage. This is the source current 2.5 milliamps. This is the current I1 corresponding to 2 milliamps, and this is the current I2 corresponding to 0.5 milliamps. So here, in order to observe the branch currents, we need to connect the ammeters. So that is what is being done, and these ammeters have to be connected in series with that particular component. Here I have connected the voltage source in series with the ammeter, whereas in these two branches I have connected the ammeter in series with the resistance. And whenever we do the simulation, we need to ensure that we provide the ground connection. Even with the discrete components, it is very much essential that you provide the ground connection. So same thing as I told you, we can provide a current source directly instead of connecting an ammeter here, and let me show that to you quickly. So what I'm going to do is I will replace this voltage source with the current source. So I'm going to place the component. I'll have to look for current sources. So the current that I require is a DC current. So I'm going to place that here. I'm going to give the ground connection common point, and the value of the current source that we required was 2.5 milliamps. And let me run the simulation and check whether the values will remain the same. So clearly you can see what I have just done is, in this multisim simulation, I have just changed the voltage source to current source, and you can see the value of the currents across the branch R1 is 2 milliamps and across that of branch R2 is 0.5 milliamps.